Hello, welcome back. I'll decorate the slides in this unit with abstract art from the northeastern part of the United States. This is Chapter 8 on Regression and Prediction. Unit 1 was Equation of a Line. We're now on Unit 2, where we'll look at the regression line. Unit 3 will look at alternate forms. Unit 4 will look at the prediction model. Let's start with Unit 2, the regression line, with this lesson. We're going to be learning about a topic called residuals. We'll also learn about the least squares criterion. We'll learn about regression constants, and we'll look at an example. In this slide, we're revisiting the principle we discussed in the prior lesson. More specifically, the principle that y and y hat express different aspects of the regression line. We can see that y hat is the predicted value of y for all people at a given value of x, but it doesn't explicitly identify their actual value. It's just the best prediction that we can make for people at that value of x. For this example, it would be people that have an x value of 4. Recall we saw in a prior lesson that there are many possible values of y for each value of x. So when x equals 4, we can have lots of people with lots of different y values. The value of y that lives directly on the regression line is our best prediction of the y value that corresponds for a person with a particular x value. But it's not the only possible value of y for a given value of x. So think back to our lessons on scatter plots. Recall that if x equals 4, it's feasible for all the people who had an x of 4 could have a y of many different values. They could have values ranging from 3 to 5 or even outside that range. We're not including all of these values in our prediction equation. And we're not including all these values on our graph. We don't have a whole scatter plot of data points, but we can imagine that they're there. In this graph, the best guess for the value of y when x equals 4 would be 5. So follow the paths of the blue lines to prove this to yourself. The value of 5 is the value of y hat, but it's not the actual value of y for all data points when x equals 4. For Alex, the xy coordinates are 4 and 6. She has a 4 on the x-axis and a 6 on the y-axis. Her data point is circled at the top blue line. Suppose the only information we have is the equation for the line, y equal 1x plus 1. The best prediction we can make for Alex's score, supposing we know her x score, would be 5. Because 1 times 4 plus 1 is 5. So this is a situation where we know her x score, but we don't know her y score. We can figure it out using the regression equation. And this point sits on the regression line. So we're computing her predicted score, but not her actual score. There's a difference between Alex's predicted y score, which is y hat, and her actual y score, which is simply symbolized with a y. We'll find a way to take this difference into account in the next set of slides. And here's how we take into account the difference between Alex's y score, which is y sub I, and her predicted score, which is y hat. We simply create the error score, which is called a residual. And it is the residual, or what we have left over after we account for the y portion of her score. So lowercase e, the residual, is equal to y sub I minus y hat sub I. In this case, the I in the equation stands for Alex, and E sub I stands for Alex's residual, which is equal to Alex's actual score of 6 minus the score we predicted for her using the regression equation. So Alex's residual is 6 minus 5 equals 1. Each person in the dataset will have their own residual. In the previous example, the residual was positive because we underpredicted for Alex. Residuals will be negative when we overpredict for a person. The black dot on the blue line in this slide is Chris's data point. So the blue line is below the red line. It has the XY coordinates 6 and 4. Chris's predicted y-score is 5, so her residual is 5 minus 4, or negative 1. We'd like to make these residuals as small as possible. So the placement of the regression line will affect the size of the residuals. We'll place the regression line so as to minimize some summary function of the residuals. So we can get an intuitive feel for finding a regression line that minimizes the residuals by using this app. And you can really have fun with regression lines, and you'll find out by if you just copy and paste the link for this app to your browser, and I'm going to show you that it's fun to play with regression lines, and I'm guessing no one's ever said that to you before. So what you do is just click on the graph, and this will allow you to add some data points to the graph. So you're trying to create a scatter plot on the graph. Notice that when you click on a spot, the X and Y coordinates appear in the window below the graph. Also notice the number of data points, or cases, or people, appears next to the n equal window. So n, recall, is the sample size. So we're going to fit a line to the points, and we're going to play with the app to find a line that makes the residuals as small as possible. So move your fit line around to make the size of the residuals as small as possible, and compare your regression line to the best fit line created by the app. Keep playing until your slope is within 0.15 points of the best fit line created by the app. So I want you to have some fun with this. Keep moving the line around and make those residuals as small as possible. And once you have them as small as you can get them, you've found the best fit line. At least it's the best fit line that you can use with just using the eyeballing technique. In the slides ahead, we're going to find out how we can find the best fit line using precise mathematical methods. So look at the equation for the regression line you've created. See how close your fitting ability is by clicking on Display Line of Best Fit. How close was your line to the best fit line? If your slope, the number in front of x, was less than 0.15 points from the slope for the best fit line as determined by the app, pat yourself on the back. You are a steely-eyed line fitter. If you didn't get within 0.15 points for the slope, keep trying until you get it. And most important, have fun. Here's the equation we'll use, and the one the regression app used, to compute the best fit line mathematically. The equation is read: the sum of the squared residuals is equal to the sum of all the individual residuals squared. The function that we choose to minimize the sum of the squared residuals on the right side of the equation. And this quantity is called the least squares criterion, or the error sum of squares, which is on the left side of the equation. Here we substitute y sub I minus y hat sub I squared for the value of e sub I squared. When we substitute b times x sub I plus c for y hat sub I. We already established equivalence that lets us do these substitutions. Note how the magnitude of the sum of squared residuals depends on our choice of the slope, which is b, and the intercept, c, of the regression line. If you want to move to advanced levels of analyses, you can learn how to compute a best fit line using partial differential calculus, but this isn't required for our course. Here are some new equations for b and c. B equals the correlation between x and y times the standard deviation of y divided by the standard deviation of x. C equals y bar, which is the mean of y, minus b times x bar, which is the mean of x. And here are some alternate forms for the slope that you can review on your own to prove to yourself that they make sense mathematically, but we won't go through these proofs just now. So let's look at an example. Given the following descriptive statistics, find the sample regression constants. So given that x bar, which is the mean of x, is 12, y bar, which is the mean of y, is 8, standard deviation of x equal 4, standard deviation of y equal 2, and the correlation between x and y, symbolized by lowercase r sub xy, is equal to 0.25. So first we have our equation for b, which is correlation between x and y, so r sub xy, times the standard deviation of y divided by the standard deviation of x. And we plug in, from the prior slide, the correlation, which is 0.25, and multiply by standard deviation of y, which is 2, divided by standard deviation of x, which is 4. Then do the algebra, and the answer is 0.125. That's our value for b. For c, we plug in y bar, which is 8, minus b. We just found that was 0.125. And then we multiply that times x bar, which is equal to 12. If you do the algebra, you find the answer is 6.5. Now we've estimated values for x and y, and we can plug those into the regression equation to get an estimated score for y, which is y hat, for any child, for Alex or Elena or Carlos, any child in the classroom, and then we can draw the regression line. Here's a graph with data points and a red regression line and an equation for y hat, which is 0.125 times x plus 6.5. You can double check for yourself that all the x values along the horizontal axis convert to the corresponding y values on the regression line when we apply the equation. When x equals 12, notice the y value falls exactly on the regression line, so the residual for this child's predicted y is 0. But for other cases, the actual y is a little above or a little below the regression line. The residuals for these children are numbers that are slightly positive or slightly negative. Here's an example to show you how to compute a predicted score for Carlos. He has an x score of 16, and his predicted y score turns out to be 8.5. In order to prove this to yourself, you can look at the equation, plug in 16 for x, and do the math. You can see that y hat, predicted y, equal 0.125 times x plus 6.5, and then 0.125 times x, which is equal to 16, plus 6.5 is equal to 8.5. So we've looked at the equation of a line. We've looked at the regression line. Next, we'll look at alternate forms. and then we'll look at Unit 4, the prediction model.